instruction set of 8086. So the next class would be how to write program using these instructions to do a certain task, a particular task. How can we do is what we can go ahead. So I request all the colleges which are taking part in this to download 8086 emulator with them, make it ready, or you can go MASM. Microsoft Macro Assembler is what you can download and keep it ready. So we can go for learning by doing concept. So here, I'll be giving a particular objective, then we together will be writing the program. So some 3 to 5 programs is what we'll try, so that you can understand the rest of the instructions. So arithmetic instructions and all the other instructions I didn't explain, but if it is explained with program, then the moment you need and then the moment you see the syntax of it, so then that would be better. So I request all the colleges, on the next Tuesday, what you do is you just download 8086 compatible to your OS and then make it ready, so that we will be writing programs so that you can practice with me and we can go ahead. Okay? Yeah. So that's why this one class little bit is what I'm just postponing, because I didn't notify this to you earlier. So now what we do is we will go ahead with the other topic, and the next class, instruction set is what we come. Keep on explaining instructions would be boring. So if you can write program, then that would be fine and all. Okay, so that's why we'll take up this particular topic in the next class. Now, in this class, what we do is we will try to take up. So now, in the last class, we'll try to take up how a system can be designed. So from my first class, I'm just taking on, the moment you try to see a programmable system, then this is what your CPU, and here in this case it is microprocessor, and then here to make or to design a system, we need to connect memory. So that memory can be any IO, or this can be RAM and this can be ROM, right? And then different IO devices need to be, input-output devices need to be connected. So as a programmer, you are writing your program in this memory using certain input devices, right? So how to design a basic system? So then we need to see the hardware point of view. We need to see the hardware point of view. So what is hardware? A thing which you can see and touch is called hardware. So now we have seen the internal details, architectural details of the microprocessor in the last class. And now what we do is, So now what we do is, we'll try to see. So then we need to know the pin diagram. So pin diagram of 8086. So you want to design a system. So then microprocessor is an IC, memory, RAM is an IC, and your EEPROM or E2PROM is another IC. So how to connect one device to the another? So this is one IC. This can be of HMOS or it can be of CMOS, and it can be of CMOS. So this can be on TTL based logic, and then this can be another logic. So when you design a system, then you need to know each and every function of these pins so that you can connect. So 8086 is a 40 pin IC, right? So this 40 pin IC, and now if you try to take any RAM IC, so then how do you connect or how do you design a system? Then you have to know the functions of each and every pins of the 8086. So this class, what we try to do is, we will try to discuss the pin diagram of 8086 so that you can connect. So here we cannot call this as connect, we call it as microprocessor and interfacing. So we call it as interfacing. Why interfacing? Here typically if you try to see this, generally it is connecting of one pin to another pin of this, but this is of different logic and this is of different logic. So the voltage levels for logic, now if it is a TTL plus 5 volts is called, we will call it as 1. But whereas if it is CMOS 3.3 volts also we call it as logic 1. So what is interfacing is connecting in a compatible manner. Connecting in a compatible manner is called interfacing. So there is a difference between microprocessor connections, microprocessor interfacing. So what do you mean by microprocessor interfacing? Connecting microprocessor with other devices in a compatible manner is called interfacing. So now if you want to design a programmable system like this and you want to interface memory and other peripherals, input-output peripherals to the microprocessor, then you should know the hardware features of it. That means the pin diagram of this 8086 need to be known, right? So this class, what we try to do is, we'll try to look into the pin diagram of 8086. Then what we do is, there are 40 pins but multiple functions. Right, so then what we do is to understand in a different easily how a system is designed point of view is what I'm going to cover in these particular classes. So the objective of today's class is to know the hardware features of 8086. Hardware means it is an IC which you can see and touch it. So if you know the pins, then you can easily interfaces. So now if you go to your labs, then you would be seeing any one of these kinds of boards. Right, this is an ESA board, generally which you use it for programming of your microprocessor. So mostly two types of boards are available in the market. That is one by Electro Systems and another one by Anshuman Pune. So if you have this in your lab, now you try to see here, this is what the microprocessor is. So this is a 40 pin IC and this entire system is designed to train BTech undergraduate students about microprocessor and concepts. So now this is in a 40 pin IC. Nearer by this, memory chips are connected. So now you can identify the memory ICs and how a system is designed. This system is designed is what we will try to see one by one. So it is important to know the hardware features of 8086 or the pin diagram of 8086. So whatever you learn here, go to the lab and then check it out, whether how they are interfaced to the 8086 And what are these ICs they are around by, which you can see on the board, is what you try to look into in the lab. Alright, so that is what the objective of today's class. So now let us go ahead with the concepts. So now let us try to see the pin diagram of 8085. So this is the pin diagram of 8085. So anyhow, this is not there in the syllabus. So now different pins and all, easy way of understanding of this, how these 40 pins they are there. If you can try to see for 8085, 8086 can become very easy. So coming to 8085, all 40 pins you cannot remember or no need to know. But if you can classify this into different signals, like you have multiplexed address and data bus, and you have control and status bus, you have external initiated signals. Like this, if you can do, it is very easy. You can identify them and then the functions of 8085. Similarly, this is the pin diagram of 8086. So here now, if you try to see, there are 40 pins in total. So this 40 pin is VCC and this 20th pin is ground. So any chip, it has to be powered up. So these are the power pins. So VCC and ground. These are the two pins generally for any ICs. So this package is called DIP, dual inline package. That means you can find the pins on both sides of the IC. For few pins on the bottom, you will get like processor of i3, i4 or Pentium processors if you try to see in the downward. So this is in 8086 is available in DIP package. So now we will try to see the hardware details of this. So let us go ahead with the first one. Here the number of address lines you have for 8086 processors are 20. So the number of address lines. So the number of address lines with 8086 are 20, and the number of data lines. So the number of data lines are 16. So out of 40, so these 36 pin will go for this address bus and data bus only. So then to reduce this, what they did is they multiplexed address bus and data buses. So now if you try to see here, you have AD0 16th pin, AD1 15th, and AD2, AD3, AD4, AD10, 12, 13 and 14. So these are the 15 pins, and here you have AD15, 16, and these are A16, A17, A18 and A19. So these are the address pins, but now they are multiplexed with the data pins. That's why it is AD, address and data, both. These pins can be used to carry address and data. So this is called multiplexing. So here now, then when you will catch, so this is called timing diagram. This we will, if you connect these pins to a CRO, then you can see these pins. Now, with reference to clock, if I speak, This is one bus cycle. We will try to see what exactly one bus cycle. Bus cycle means what? Like, if you want to do a memory read operation, means one byte you read from the memory, execute, decode and execute, then it takes 4 clock cycles. So this is T1, the first clock cycle. This is T2, T3 and T4. In 4 clock cycles it takes. So this is one time period T1. So the processor here has one more pin which is called ALE, address latch enable. So the 25th pin here is ALE, which is called address latch enabler. So the processor generates ALE signal, which is a high signal, during T1. So that then, see, these two pins are there, multiplexed. So then when they will carry address, when they will carry data is what need to be seen. So here if you try to see, the processor during T1, it generates a signal ALE, which is used to demultiplex this address bus and data buses. That means these pins will carry address during the first clock cycle. That means, to see in detail, if your processor is working with 5 megahertz clock, okay, your processor, if it is working with, so there should be a clock signal here. So the 19th pin is a clock pin. So here you are going to connect the external clock. Any digital IC has to be driven by a clock. So this clock you are giving, let us take that is 5 megahertz. Then each time period would be 1 by 5 megahertz. That would be 0.2 microsecond. So this is 0.2 microsecond. This is 0.2 microsecond. This is 0.2 microsecond. This is 0.2 microsecond. So during the first clock cycle, means up only 0.2 microsecond, the processor will places the address from where it has to fetch the instruction. And then during the second clock cycle, these address, right, that means the processor will place addresses on the address bus only during 0.2 microsecond if it is working with 5 megahertz. Then if it is with, right, and then after that it will carry the data. So here, so how to make this address available for the whole bus cycle? That means the address is available during only one clock cycle, but the byte has to be fetched, decoded and executed. That takes 4 clock cycle. So how, up to that particular point, that few devices, processor is working with megahertz, memory would be working with millisecond. Memory access time of a memory would be millisecond. So memory will be slow responding. When processor is needing a byte, then it may take milliseconds to put the data on the data bus. But up to that particular point, the address should be decoded and then pointed out to a memory location. So how to make this address available for whole bus cycle means, this can be done by using a concept, demultiplexers. You need to, that means address should be carried for rest of the 3 clock cycles, and then what we need is, we need a device which will hold the address. Then the holding can be done by using latch. So already we have seen in our digital system design or digital ICs, this latch holds the data, right? If you give here 1, truth table of D flip-flop, if you try to see, if you give here 1, then you will get here 1, right? Then when there is a clock, then the 1 will be present, and until the next clock change or the next change data, the same thing it would be present. So latch holds the data. So the internal circuit of this already you have seen in your earlier classes. So this is the latch. So what we do is to demultiplex the address bus from the data bus. That means address should be there for whole bus cycle, but processor is giving the address for only for 0.2 microsecond. Then we need to separate the address and data. So then that can be done by using connecting a D flip-flop, right? So now if you try to see here, ALE is connected to enable, and so here if you try to see this, I will try to show you the IC, and ADs, one of the ADs is connected to D. That means here if there is a microprocessor, AD0 can be connected to D, and enable is connected. That means ALE is connected. That means ALE is connected. During the clock cycle, whatever the data is there, this data will be connected. So ALE is connected to the enable, right? So now if you try to see how many address lines we have, 20 address lines we have. But how many they are multiplexed? 16 they are multiplexed. Right, 16 data lines are there, and then other pins if you try to see here, other pins if you try to see here, these pins 36, 37, 30, 36, 37, 38 and 35, they are address and status lines are also multiplexed. So to around 20 address lines need to be demultiplexed. So we need D latches. So here for one line you need one AD0. Demultiplexing means you need one D flip-flop. So similarly you need 8 D flip-flops. So then this 8-bit D latch is available in the form of a IC. So this IC is 74LS373. All these things you will see in your lab on your kit. 74LS373. So this is an octal latch, like 8-bit data latch it is. So inputs are D0 to D7. So D0 to D0, D1, D2, D3, D4, D5, D6, D7. And outputs are O1, O2 and all. So this is the pin. So one latch can hold the addresses up to 8. Total how many lines we need to do? The total how many lines means 20 lines. So we need 3 8s are 24. 2 latches if we use, 2 8, 16. 16 address lines only we can demultiplex. But whereas if you use 3, then 20 can be demultiplexed. So this is how they are connected as. So this is what your 8086 processor, and this is what your ALE 373 IC. If you try to see, you have a pin called enable pin, which is 11th pin, right? So ALE is connected to enable. So how many latches you need? 3 latches you need. So lower address lines AD0 to AD7 are given to one latch, and AD9 to A15, right? AD8 to AD15, AD0 to AD7, these are 8 lines are given to one latch, and AD9 to AD15 are given to another latch. So here if you try to see, this ALE is a logic high signal. During this time, whatever is the data present here, address present here, will be latched by this particular address liners until, that means until next ALE, it will carry the same data. So A0 to A15, and here you have A16 to A19. Then you need one more latch here. And you can demultiplex the address and data buses. So almost we are covering in Venn diagram. When you try to connect any other memory or input output devices, first of all, the task you need to do is you need to demultiplex your address and data. So what do you mean by multiplexing? To reduce the number of pins of a processor, a single pin can perform multiple functions. So in first clock cycle that will carry the address, during the next clock cycles it can carry the data. So, but address is needed for whole 4 clock cycles of the bus cycle. So then we need, the first task we need to do in designing of the system is to demultiplex the address and data buses. So this demultiplexing can be done by using 74LS373 is the latches, right? So 3 latches and the physical connection is. So here if you try to see, ALE is connected to G and output enable is what is one more pin. If you try to see latch enable, right? VCC, ground. Right, so this is what 74LS373 octal D latch. Then it is a 20-pin IC. So then 20-pin IC, if you try to see, this enable is what you connect to your, this thing is output control. One is output enable. So this is OE is what you are trying to connecting it to ground. So this is how you do demultiplexing this. So here you have 3 latches. So this is what the demultiplexing concept. So now here during the read cycle or write cycle, so after demultiplexing this, so here between the processor and the memory you are connecting a latch. So this address is valid for whole clock means bus cycles, whole bus cycles, right? So then the address, the processor is placing the address in only T1, but because of we are using latches, the address is a valid address is available up to T4 also. And then the next one, the next clock cycle is that those pins can be used to carry the data, right? So now coming to the 8086 pins, VCC and ground, so 3 pins are, 2 ground pins are. Then you have clock, just now we discussed about the clock. Then you have the reset. Then you have minimum and maximum. This is what very important thing is, minimum and maximum, MN by MX. Right, this is ready, each and every pin is what we need to know. That is what the pin diagram description of 8086. NMI is a non-maskable interrupt. Right, so these are the pins. Now if you try to see, few are, this is how you can know, okay, this can be done. So now let us try to see the each and every pin function is. Right, so now if you try to see this, what is this minimum and maximum minimum mode and maximum mode means. Now let us try to see, we are trying to design a system, then designing a system can be checked on a bottom-up approach. So bottom-up approach means we can study the computer architecture by starting with basic building blocks, transistors and logic gates. Then to build more complex circuits, we need flip-flops, resistors, multiplexers, decoders and adder, from which we can build computer components like memory, processor and bar. So this is what the top-up approach. So now we are going ahead. So coming, if you try to see the bus structure, this is what your pin diagram of 8086. So minimum mode of operation means here the 33rd pin here. This is very important. So the 33rd pin here. So that the 33rd pin here is minimum by maximum. If this pin, if it is connected to 5 volts, then it will act in minimum mode. If it is connecting to ground, then if it is connecting to ground, then if it is connected to ground, then it can act like in maximum mode. So minimum mode of operation and maximum of mode of operation is just by connecting. Yeah, this is what we have seen up to now. And yeah, so now here in minimum mode and maximum mode, if you try to see this pin, the minimum and maximum, the 33rd pin. So this is how in minimum mode how the pins they look like this. So here the 33rd pin is connected to VCC, means it is in minimum mode. So what do you mean by this minimum mode and maximum mode of operation is, let us take if the processor has to do some floating point operations. So then it takes longer time, the processor takes longer time to do floating point operations. Then what it does is, it will accommodate one more processor, like co-processor is what we call 8087, and it can work, that means it can work alone or it can accommodate one more processor. So when it is accommodating a submaster, right, so then that is called, it is working in multiprocessor environment is. That means it is accommodating other processor to task to be done. This is called multiprocessor environment is. So in maximum mode, you can connect one more processor 8087 and you can work. Then that is called maximum mode. That means the 33rd pin, if you connect it to 0, yeah, then it is in maximum mode. So the maximum mode means what? It can accommodate multi-processors. That means co-processor it can act to do floating point operations. So we'll try to see maximum mode a little later. Now we'll try to see the minimum mode of operation. That means when it is connected to 5 volts, the processor working in alone mode is. So in minimum mode, if you try to see, and this is connected to VCC, means it is in minimum mode. Now if you try to see this AD0 to AD15 and A16 to A19, and here you are using latches. These latches can be of Intel made ICs like 82C82, or it can be of 373, which we have just now seen. So 3 latches is what we need. So then demultiplexing is done. So then after demultiplexing, the address is available, and here you are going to connect your memory ICs, right? So this is CMOS RAM, and then this is CMOS RAM. So you need, here in memory segmentation we have seen, like the memory which was going to be connected to 8086 processor is going to be divided into even bank and odd bank. So that means 2 RAM chips need to be connected here for 8086. That is what we have already seen, the advantage of segmenting memory into even bank and odd bank, because within a clock cycle you can get a word. So here you have 2 RAM ICs, and then here you can have one PROM. That means your booting instructions can be stored in PROM or E-square PROM. So you need 2 PROMs and then 2 RAM ICs to design this particular system is. So now here when you go to the lab, very clearly you see, so these kind of things, when you try to see here, this is the board. When you are trying to see, try to identify these ICs so that how they are connected you can easily understand. This is what your 8086 processor, and very nearby you can find HY62256 is Hyundai memory ICs. You identify HY226 where it is, that is what 2 RAM slots. Why you are using 2 RAM slots? Because 8086 memory is connected into, or it is divided into even bank and odd banks. And then here if you see this, there is a paper pasted ICs. Means these ICs you can identify it as E-square PROMs. EPROMs or E-square PROMs, you can try to see here. what it is, the moment you connect it, then you may get VI microsystems or Anshuman, some kind of thing. So those booting instructions are stored here in this E square P dot. So you need to connect two, that means two ROMs, two EEPROMs, and then you need to connect two RAM slots. You just check it out in your lab by going. So here two RAMs and then two EEPROMs what you need to connect. So the moment you are connecting these things, you are trying to connect this with the help of, and then nearby you can find 74LS373 latches. Identify here 74LS373. That means you need 3 latches to demultiplex address and data bus. Right? So now that is what you just try to see how a system is designed. This is how you get interest. So then two EEPROMs and all, then the architecture, how it is connected is like this. So this is 373 after latch. So here, then and here you have one more. So this is what, here you have 3 latches by which you are connecting. Here you can write, 2 ROMs, EEPROMs, and then 2 RAMs, they are connected. And here you need to know one more pin, which is DT by R bar and data enable. So these are the pins. Read bar and write bar is what you need to know. So now let us try to see the details of those particular pins, and then we can come back. So now here if you try to see, few pins like here you have write bar and read bar. This read bar and write bar, these two pins, when the processor is doing a reading operation or the processor is doing a writing operation, these two pins used to indicate the processor, now if you try to see, this is read bar. If this pin is low, means the processor is reading a byte into the processor. And if this write bar, if it is low, then it is writing a byte into the memory or an IO. Right? Okay, so these two are the read bar and write bars. So there is a pin here, DT by R bar and data enable. This is very important to know, because the hardware, the design consideration, when you are going to see these two pins, you have to know. Then there is one more pin called M by IO bar. The processor is reading a byte from a memory or IO. It can do. So then that can be done. So the status can be indicated by using M by IO bar. This is logic 1, means the processor is reading a byte from the memory. That means it is doing a memory operation or it is doing an IO operation. So the processor is doing a memory operation or the processor is doing an IO operation can be identified by using M by IO bar pin. And read bar and write bar is what we have seen already. And this I'll try to discuss a little later. Non-mask control interrupt. So these are interrupt pins NMI and INTR, and there is data enable, and then ALE already we have seen. Then we will discuss these pins a little later. So now let us try to see this read bar, write bar, and M by IO bar. So here, using these pins, whether the processor is doing a memory read operation or a memory write operation, or IO read operation or IO write operation, these 3 pins in combination will give. So if read bar if it is 0 and write bar if it is 1 and I0 by M bar if it is 0, then the processor is doing IO read operation is. So these 3 pins together will indicate which task is done by the processor. So if read bar if it is 1, write bar if it is 0, and I0 by M bar if it is 0, then it is IO write operations. And if the read bar if it is 0 and write bar if it is 1, so anyhow read bar is 0 means it is doing reading operation, but it is M. That means it is M. I0 by M bar is 1 means it is doing memory read operation. And if read bar is 1 and then write bar if it is 0, then I0 by M bar if it is 1, then it is doing memory write operations. If both are 0 and then whatever it is I0 by M bar, it should not happen because processor can do either memory read operation or memory write operation or IO read operation or IO write operation only. So then we need to generate these signals. So these signals can be generated by using this kind of logic. So to do the memory read operation or memory write operation kind of thing, so then this input side you have read bar, write bar and I0 by M bar. Then here you can consider this as an OR logic. So how to generate this? Now you see whatever we have seen in this table. Now when it is 0 and 1 can be achieved through this. So when it is 0 and when it is 0, so when it is 0 and 0, then this is 0, the simple logic or logic. So then this is 0 means this is doing IO read operations. This is how you design this memory read and IO write this. All these things I will try to show you. And now this is, this is an OR logic is what we need. Then 74LS32 is an OR gate is, right? So then this is 74LS04 is NOT gate is. So here when you try to see nearer by this memory read and memory write, you can find few OR gates, means why they are there is what you need to understand. Okay, so this is 7432 IC, then 7404 IC is. So now if you try to see the one bus cycle, then now you can try to see. Here you have memory read bar. Memory read bar means what? It is a combination of all these things. Is what you can understand is. Then the next one. So this is about memory 3 pins is what we try to discuss here. Read bar, write bar, I0 by M bars. And this indicates the processor's task. Okay. Then next one is BHE by S7. This BHE is valid during T1 only. This is bus high enable. This is also very important pin. This is bus high enable is produced by it is generated by the processor during T1 only, and it should be latched like required address bin. It stands for bus high enable. And which bus high enable? That means you are doing data bus. Right, and what do you mean by high? That means the higher half of the data bus. So that means here you are connecting two memories banks or two memory banks, even bank and odd bank. Then lower byte or higher byte is what you are trying to fetch. So then that can be indicated by using bus high enable. So if you have two memory chips of RAM, okay, two memory chips of RAM, then lower byte of this, that means this memory, from this memory you need to get the data, na? So then this memory enable is what we call chipset. So this chipset is, when it is going low means this memory is enabled. So here you have, yeah, so this is what is. So there are two another pins you need to understand. One is bus high enable. So here you have chipset and here you have chipset. So if it is higher byte has to be enabled, means that higher byte BHE of the microprocessor pin is connected to chipset of or enabling of this particular memory is. So you need two signals like A0 and BHE for enabling lower byte or higher byte. Using 8086 processor, you can do a byte operation or a word operation. So a byte you can fetch even from the even bank, a byte you can fetch from the odd bank, or a word you can fetch. So these two signals A0 and BHE. A0 is what? A0 is the 0th address pin of the 8086. This A0 is used to enable the lower half of the data bus, and this is called bus low enable is, bus high enable, bus low enable is. So now if you try to see here, This bus high enable, if it is 0, that means the pins, you have to keep that in mind. So the BHE, if it is 0 and A0 if it is 0, then the processor is transferring 16 bits of data from both ICs. And if BHE is 0 and DLE is 1, then only 1 byte will be transferred, and that is from R band. And BHE if it is 1 and A0 if it is 0, then you are getting a byte from the lower bytes. And 1 and 1, no bank is enabled. That means no data you can fetch it. These two pins are very important pins. So then now if you try to see, this is very important, just keep in mind. Now you try to see, here you have a memory, here you have a memory, and this is even band, this is what R band is. So now if you try to see, this memory need to be interfaced. This memory need to be interfaced to your 8086. So then what you do is, this memory is of 64K by 8. In your lab also, I think 64K or 128K RAM slots are available. If it is 64K by 8, then the address bus, now if you try to see A1 to A16, right, 20 address lines, 20 address lines to do. So here you have A0 to A50, right? So the address lines you will connect here, and data lines D0 to D7 of the processor you connected to even band, and D8 to D15 from the processor you connected to the odd band of the odd band is D0 to D7 is. And address lines are, so this is no 20 address lines. It should be A0 to A20. This is not A16, so it is A12. You can start from A1, right? So you will use some memory decoding circuit here for enabling one particular memory addresses. And now, just now we have seen how to generate this memory read and memory write. So this memory read is connected. So these are the pins of your 8086. I told you I started this class like this. In this class, we are going to see the hardware details. So hardware details means, which you can see and touch. 8086 with memory, how you are connecting, you should know. You can see it, right? So now the hardware, the pin diagram of the memory IC, if you try to see, very important pin are write enable, and this output enable and chip select. These are the pins. So the chip select means what? When this chip select is 0, then you can access, you can read a byte or you can write a byte. Now this chip select is connected to A0 pin of even band, and chip select of the second pin is connected to bus high enablers, right? So then if it is 0 means the processor is doing on, it is carrying D0 to D7, it is carrying D8 to D15, a word operation, a byte operation or something. So this is write enable. That means you are doing memory read operation. So memory read operation is connected here, and memory write operation is connected here to write enable. Memory read operation is connected here to the output enable. So this is the memory interfacing to the 8086. It's very, very important. So then here in this case we have seen 5 pins up to now. One is read bar, write bar, and I0 by M bar, and how they are used. And another 2 pins are A0 and DHE. So this A0 and DHE indicates the processor is doing a word operation, or the processor is doing a byte operation, or the processor is doing byte operation, or the processor is doing is what? That means fetching from a lower byte or fetching from a higher byte. On which byte it is operating is what you can understand. So these are the another 5 pins of 8086, right? So then The memory which is connected to this is called odd memory and even memory. Already this we have seen. And the even memory is even because it contains bytes that carry even processor address and odd processor addresses. And write read operation. So here 1 and 1 means no memory operation is what you can consider. Data pins in use, you can identify like this. And 1 or 2 bus cycles. That means here when write read a word at an even address means the data pins used are BHE and A0, and you see in the previous slide 1 bus cycle is enough. Right. So, but fetching that means this is where another point where 1 byte when you fetch from even bank 1 clock cycle is enough. But 1 byte if you fetch from odd address, then you need 2 clock cycles. The meaning is this of this particular slide. So then the next one is the next pins are status pins. Right. This next pins are status pins. So the status pins are S6. Yeah. S3 to S6 and they are multiplex with this address lines. So this S3 to S6 what they are, now let us try to see. So they are the least important pins and they are rarely used. We are not going to, they indicates only the status, and in the maximum mode of operation you are going to see. So at that point I will try to cover these things. So S3 and S4, then if they are 0, 0, then extra segment, 0, 1 is stack segment, 1, 0 is code segment, and 1, 1 is data segment. So one possible application of S3 and S4 that is usually mentioned address for 1 megabyte. I'll try to cover it, and when I try to cover this in this thing. So this is minimum by maximum mode pin. Just now we have seen. So when it is connected to VCC, then here one more important point you need to note. So when it is in minimum mode, then this 31 pin to 34 pin, they act like hold, acknowledge, write bar, M by IO bar, DT by R bar, data enable, ALE and R. But when it is connected to 0, right, when it is connected to ground, in maximum mode here, these the equivalent signals of this thing has to be generated, that we will try to see in maximum mode of operation. So this is minimum mode and maximum mode of operation. Right? So now coming to the minimum mode signal, these are the another minimum mode signals and important signals. And here this hold means hold and hold acknowledge. These are used in direct memory transfer. Now you want to transfer huge data from memory to from your computer to pen drive. This kind of example you can consider. You want to transfer your data from pen drive to your hard disk or hard disk to pen drive. So then if the processor is involved in this data transfer, then processor will be transferring the data, but it is in IDL. Then what it does is it will use another controller called direct memory access control. So then direct memory access control is one more submaster. So then which will do this memory transfer. So then now let us try to see here. This is what your microprocessor. So this hold and hold acknowledge pins functions is what we are trying to understand. So now this is your microprocessor, and then here is what your DMA, right, and direct memory access, and now here is your memory, and here is what your pen drive or IO. So now if you want to transfer the bytes, huge bytes from this memory to IO, then that is done through DMA. So then DMA, what it does is it asks the buses of the processor, microprocessor, address bus and data bus. It want to use address bus and data bus of this to transfer directly from memory to IO. So then what the DMA processor does, DMA controller does is it puts a request called hold. That means you hold for some time. It requests the processor to hold for some time by placing a 5-volt signal on this particular hold pin. So then if the request is valid request, then the processor will use the hold acknowledgement hold acknowledgement, and yes, he says yes, you can go ahead. So this hold and hold acknowledge are used in direct memory access applications. And already we have seen this write control I0 by M bar. And here there is one more pin, ALE already we have seen. And DT by R bar is data transmit or receive. What that is now, let us try to see. Okay. So now coming to my previous slide, the minimum mode of operation, if you try to see here, yeah, now you can identify these pins which we discussed up to now. This is in minimum mode of operation. This is read bar and write bar and M by IO bar in combination. They are going to be connected to read pin or write pin, and then M by I0 by bar. This is M by I0, so that means if it is memory operation, then this is connected. This M by I0 bar should be connected to this thing. Now if you try to see here, you have BHE, bus high enable, and then here you have A0. So this bus high enable and these two things, be a bus high enable should be connected to odd bank of the memory. So now you can see here. So this is minimum mode of operation of 8086. So this is bus high enable. So this bus high enable should be connected to all the memories. That means that is fetching from even bank or that is fetching from the odd bank. And this chip select, okay, this chip select of each pin should be connected. Now already I have shown you in my previous slide where it has to be connected. It has to be connected to A0 by A0 and BHE. So A0 pin and BHE pin should be connected to these things. So here you have A0, right, A0, and then here you have BHE. These two things are connected to RAM slots and then ROM slots, right? And now that is what the connection is. See, once you know the concept, then there is no need of by hearting kind of thing. So here, these are the pins we are trying to discuss here of the 8086s. So this AD0 to AD15 and A16 to A19 are given to latch, and 20-bit address is available here. This is latch, and here we need buffer. So why buffer is required is what we'll try to see. This is 74LS245 R82C85 Intel IC. This is Intel made IC, which is a buffer IC. So what do you mean when you need a buffer? When processor is doing a memory or IO operation, that means from memory to the processor or processor to memory, when you are connecting external devices, then the pins of 8086 need to be protected. That means protected means here what? This is an IC, this is an IC. So any current, when one is carried by this data bus, then that pin can be getting damaged due to the current sinking. The current sinking capability of this particular pin, if it is not within the range, then there is a possibility of getting the pins of 8086 getting damaged. So what we do is we will use buffer 74LS245 buffer. So here we use two buffers to isolate this particular IC from 8086 processors. All right. So if you try to see the buffer IC and buffer IC configuration, so this is what the buffer IC 74LS245 is. And internal diagram of this, if you try to see, so this is buffer. Buffer means it connects your input to a high input impedance, low output impedance is what you can describe the buffer is 74LS245 is. So here you have a pin called DIR, and here you have chip enablers. That means when you are, so this side you are connecting your memory, and this side you are connecting when you are designing a simple system, and this side you are connecting 8086. So when memory read or memory write operation, when it has to be performed, So then data direction should be known. The data is from memory to the processor or processor to the memory. Same pin A0 and B0, they are there, but the data is controlled through this direction pin. So A0, the data transfer has to happen from memory to the processor, processor to the memory, or memory to the processor. That can be given by this DIR. So this DIR, another one is chip enable. So you need here two signals of this 245 when it is connected between your processor and the memory. So the here you have DT by R bar and data enable. These two are the signals. So these two are the signals are connected to DIR and CE bar. So data enable means the moment you want to transfer a byte from the memory, so the memory is interfaced to the microprocessor through 245. So then the memory, this enabling task, that means enabling a memory is done through data enable pin. When it is low, then this chip select is selected, then this 245 buffer is enabled, right? And data, how it should be transferred. This DT, if it is 5 volts, then processor to memory it will go ahead. And DT by R bar means the processor is receiving the byte from the memory. So it is very simple to connect this buffering and multiplexing. So be clear with this. Okay, be clear with this. This logic, being an electronic engineer graduate, you have to design a system, a simple system, a programmable system, which is based on 80 or 8086. Then these things you can see in your lab. The moment you see the kit, you can find 245, 245 because here even bank and odd bank. So 2 buffers you need, 3 latches you need, and the connections are this. And it should be AD02. It is I have taken this from a book. So this is AD02, AD90 I will say AD16, and then these are things how they are connected. So this is what bus buffering and demultiplexing is. So now if you try to see the minimum mode operation of 8086, now clearly you can see like here DT by R bar is connected to the latch. If it is 373, it should be connected to DIR. And data enable is connected to chip select. That's it. And output is data, that is of 8-bit or 16-bit from your memory or IOs. So that's it. This is what the minimum mode of operation of 8086 and its pins of working of these pins of processor in minimum mode of operation. Is this clear? So this is what the hardware details of 8086 is. So now once you do the interconnection, like once you do a connection like this, see, and we will try to see the other signals also. The clock signal here of 5 megahertz is generated by using another IC called 8284. 8284 is a clock generator IC. A crystal is connected to clock generator IC, and then you will be getting clock, ready, and reset signal from this clock, right? And this is what the simple way of drawing is. So how a memory read operation can happen? Now let us try to see this with the help of logic things. So now in memory read cycle, what happens? So be careful, pay attention and try to understand this. Right. So now are you with me? Now let me see how you are. Okay. Are you following me? Yeah. So now let us go ahead. Right. So up to now we have seen the minimum mode and maximum mode of operation. The minimum mode of operation is now how generally the processor reads a byte from the memory. So now we have seen the hardware details. Now let us try to see how it works. See here the clock of the processor, if you connect it to a oscilloscope, right, 30 megahertz is what is available in your lab. So you can connect and then you can see the pins like this. So the processor places the address during the first clock of this. So this is what, so here in first clock the processor places the address, then processor releases a signal called ALE during the first clock cycle. So now you try to see during the first clock cycle, the processor generates this ALE. And during this time, the bus address is available. And now if you try to see M by I0 bar, that means this is a memory read operation, then it should be high. M by I0 bar, that means you are doing memory read operation. So that's why it is high for one memory read cycle. So this is one memory bus cycle is what you can consider. So here you have to know the terms like this. You have to know a clock period and you have to know one memory read cycle, machine cycle. Okay, you have to know the machine cycle. So 4 clock cycles are called one machine cycle, and the time taken by the processor to read a byte from the memory or write a byte into the memory is called one memory read bus cycle. So that's why only 4 clock signals is what we are trying to show. So now here the memory read bus cycles, when you are trying to understand, here you have the clock period, so 4 clock period. So this period to this period is what you are showing. So during the first clock period, the processor releases the address from where it has to fetch a byte. Okay, and then after this T1, this data will be, so the data will be at a high or high impedance state, but data is available during T3 and T4 state. So data address. So then here only you have to write this. This is ALE, draw this, and M by I bar should be high. You are doing memory read operation. So data is not available during T1. The data is available T2 or off of the T2 to T3, T4 cycle. So that's why read bar signal, that means go low, indicating that it is reading a byte. So the byte is available during T3 and D4. So during this time it will goes high. And dt by r bar. So here what should be the dt by r bar? So memory read operation means from memory you are fetching a byte. From memory when you are fetching a byte, so then the data is into the processor. So into the processor is indicated by using R bar. So that means when it is low, like when it is low, so then the data comes in, and this is given to DAR pin of 245 so that it allows the data into the processors. And data enable should be, so here data enable, when it is low, right, when it is low means that to the buffer it can do it. This is what the read timing is, right? So one cycle of this clock is called a state, and one cycle of this clock is called state, and state is measured from falling edge of the one clock to falling edge of the next clock. And if clock is 5 megahertz, then the T state is 200 nanoseconds. The clock is 10 megahertz, then it is 100 nanoseconds. So a basic microprocessor operation such as reading a byte from memory or writing a byte to a port is called machine cycle. So we define a cycle called machine cycle. The time taken by the processor to do a memory read operation or memory write operation is called one machine cycle. And the time A microprocessor requires to fetch and execute an entire instruction is referred to as instruction cycle. Be clear here, you have a state or a cycle or a state, machine cycle and instruction cycle is entire instruction, the time taken for the processor to entire instruction fetching, decoding and execution is taken as instruction cycle, and the machine cycle means to do a memory read operation or memory write operation, how much time it takes us. So here you can try to take this input bus cycle here. So in minimum mode of operation, what happens is, and this is what the logic signals available at different pins indicating how the processor is working. So I summarize. So memory read operation means, thoroughly we have seen here, this is memory write cycle. So memory read cycle we have seen. Memory write cycle means this is the clock you can consider. During the first clock, the address is available. This is a D0 to, and this is total, total 20-bit address, and ALE I0 by M bar. So memory write. So memory indicating memory. This is 0, and write bar means it is doing writing operation. If it is memory read operation, then you have to consider about read. If it is write operation, then you have to consider about write. And then data DT by R bar, data enable. So these are the signals you need to consider when processor is doing a memory read cycle or a machine cycle. So I summarize. Today what we have seen is, we have seen the hardware details of the microprocessor, what are the pins are with 8086 microprocessor, and we have seen what is multiplexing and how to demultiplex the address bus and data bus and status bus. Then we have seen the processor works in two environments. One is called minimum mode of operation, another one is called maximum mode of operation. So minimum mode of operation means, the processor is working on standalone. In maximum mode of operation means the processor can accommodate a coprocessor. A processor can accommodate a coprocessor, right? So that is by using a pin called MN by MX bar, right? So in minimum mode of operation, what are the signals? To design a system, simple designing of a system is what we have seen, right? So, and what are the signals related with this one memory read operation is what we have seen. So then now today you go to the lab and try to see what are all the things we discussed here, whether they are available or not. So you should be very particular to identify the microprocessor, to identify the memory ICs, to identify RAM and ROM ICs, then to identify the 373 ICs, 74LS373 ICs, to identify 245 buffer and how they are connected. Anyhow, this is in printed circuit board. You cannot identify, but at least you can try to see what exactly they are there in the board is. So this is minimum mode of operation, and we have seen memory read cycle, on machine cycle, on instruction cycle and all. So in the next class I will be trying to take up the programming part once this hardware is known. So the programming part is what we can see. So then we will be meeting in the next classes. All right. So this is what for today's call.